Hi everyone, thank you so much for joining us today for our guest speaker session. We have with us Zechun. Zechun is a senior researcher at Meta with research interests in large language model and machine learning efficiency. Her research has been published in top-tier conferences and cited over 4,000 times. Today she'll be talking about efficient deployment of large language models, including mobile LLM and SpinQuant. Thank you so much for taking out time, and I'll pass it over to you.
Yeah, thank you, Amit, for introduction. Hello, everyone. I'm Zechun Liu, and I'm going to talk about mobile LLM and SpinQuant in today's presentation. Okay, then let's get started. So at the beginning of this year, our team has been working on optimizing the LLMs to operate efficiently on devices such as smartphones and wearables. And we want to keep their precision as much as possible when we optimize these small models. And to accomplish this, we develop some architecture designs tailored for those smaller LLMs with sub-billion model sizes. Those architectures, like those architectures proposed in mobile LLMs, are specifically designed to considering the constraints of the storage limitation in the edge devices. And since the release of mobile LLMs, there are a lot of great works also working on this on-device use cases, such as stable LLM, Q1 2.0. These are all very great works, and since they are released after the mobile LLM, in today's presentation or in mobile paper, we didn't compare with them. So, so the questions here, like we want to ask for the mobile LM, for the on-device LM is basically first, why do we want to put LLMs in on-device? And then second, how can we run it on device? And what are the constraints? And the third, what is the capability of the smaller models, how good it can achieve in various tasks. To answer those questions, we just go into the details. Contemporarily, those LLMs like ChatGPT, they primarily operate on the cloud environments. However, there are growing needs for running LLMs on portable devices such as smartphones, watches, and AR/VR glasses. It requires smaller models, and these devices have limited memory and computation resources, which requires a special designed LLM to meet the constraints. For example, the memory hierarchy of the mobile devices can be seen in this figure. So DRAM capacity of a phone could range from 6 GB to 12 GB. And since the DRAM is shared with operation system and other applications, a mobile app should not exceed 10% of the DRAM. Therefore, we are motivated to develop the 7 billion-sized mobile app that can efficiently utilize the limited resources available on those devices. And still delivering high quality results. So by doing so, we can enable a more efficient on-device language assistant, which has the potential to revolutionize the way we interact with our devices. So previous LLMs are not optimized under this model size constraints, and which results in suboptimal performance. For example, the OPT and GPT-NEO, it was designed for hundreds of billion model parameters, and the sub-billion models are only an intermediate byproduct of the larger models, and the surpassing is an analysis suite, and it is not particularly designed architecture for small models as well. Therefore, to fully exploit the potential of the sub-billion models sizes, sub-billion models, we should carefully tune the architectures and utilize the weights more effectively. And the result shows that after our careful design, mobile LLM can achieve much higher accuracy compared to the previous works. So what we did for so what we did for mobile LLMs in the design of the mobile LLM, we first experimented various techniques proposed in the super billion parameter models, on those large models, and we found out three techniques that are very beneficial for the super billion size models, including the sweet glue, embedding sharing, and the group query attention. We built a strong baseline by integrating these techniques. And additionally, we found that use deeper and shallower architecture can help further improve the model performance, and it's more favorable for the on-device small models. And we also developed the immediate blockwise layer sharing method to further boost accuracy without increasing any model size. So now let's step into each specific design details, and let's see how they contribute to the overall accuracy. Uh, First is the sweet glue. We follow the Llama paper to use sweet glue in the feed-forward network. Um, like OPT models, those contain small model designs, they use the vanilla FC, real FC structure. And we found that by replacing this FC, real FC to Swiggle can boost the average performance by like 1 to 2 points. Um, and then and since this, we found that deeper network is more favorable for small models. And although there is a proven belief from the scaling law paper suggesting that the large language model performance is primarily determined by the number of parameters, the training data size, and the training iterations, meaning that the architecture difference doesn't matter for the final accuracy. However, we find that for the smaller models, it is not the case. Architecture do matters for the performance, and we can see that we conduct a study involving training of 9 models with around 125 million parameters and 10 models with around 350 million parameters, each designed with similar size but varied in terms of depth and width. Our experiments consistently show that deeper and thinner models outperforms their shallower and wider counterparts, like on those 8 zero-shot common sense reasoning tests, and as well as those question answering and reading comprehension benchmarks. Uh, as we can see in the figure, the red lines representing the deeper networks almost always outperform those green lines denoting the shallower networks. And in addition to that, in billion scale models, the embedding layers make up a substantial proportion of the parameter count. For example, in a 125 million parameter model, the input and output embedding each have like 16 million parameters, and it can account for over 20% of total parameters. However, the proportion of the embedding width size is significantly lower in large language models, such as Llama 2 7B and Llama 2 70B, which only comprise 4% and 4% of the total parameter in the 7B model and 1% of the parameter model in 70B. So, this difference may explain why the embedding sharing is not used in Llama 2 series, but it's important for the smaller models. And we note that in Llama 3 series, especially in those small 1B, 3B models, they also use the embedding sharing now. And in the also, then in the sub-billion scale language models, we just use the concept of embedding sharing, and by sharing the embeddings, we can reduce the number of parameters by 12%, and it only sees a marginal decrease of 0.2 points. And also, this embedding sharing can further can also improve the training stability. And then after embedding sharing, we can use those reduced parameters in other where, for example, we can increase the depth, and it can further boost the accuracy. Mm. And additionally, we can incorporate the group query attention into the baseline model design. These techniques can be seen as another form of weight reutilization, and the number of query heads is n times of the key value heads, and we can repeat the KV heads by n times in computing the attention score. So by reducing the number of KV heads to a quarter of the query heads, we can achieve a significant 10% reduction in the model size, and while we only experience a less than 0.2 points drop in accuracy. So this can further save us more parameters in small models. And then lastly, recall the findings, we suggest that a deeper network is more beneficial for small models. So we want to find a way that we can increase the deep depth without introducing any additional parameters. Then layer sharing comes as a very good solution. And we tried layer sharing. This indeed can amazingly improve the accuracy, and just by repeating the block twice, just we store one block and we compute it twice, it can amazingly increase the accuracy. So we further investigate 3 different weight sharing strategies. For example, showing this figure, we investigate the immediate blockwise sharing, which is shown in figure B, and we can repeat the whole network, repeat over the full network, and also we can reversely repeat the network. And the experiment results shows that those they achieve similar results. The repeat overshare achieves slightly better results than the other 2 methods. But however, considering we want to utilize the data locality, which means in actual decoding time, the most costly part. By costly, I mean most latent, consume most latency part is the weight movement, which means we want to move the weights from storage to the compute engine. This part is consumes the most latency. So we want to utilize data locality by moving the weights once and immediately compute it twice. So we choose this immediate blockwise share to boost accuracy and without compromising too much latency. And then the final result shows that our performance can largely improve previous works like MobileLLM 125 million. It can achieve much better accuracy than the OPT 125, GPT Neo 125, and also even achieves better results than these 160 million models. And for the similar trend we can find in the MobileLLM 350 million models. Also in our updated version, we also include more sizes ranging from 16 million to 16 million 1B and 1.5B models. Those models are all released on both GitHub and Hugging Face. You can download it. And so for the latency, and we also measure the latency on the MacBook CPU, and we can see that the MobileLLM can execute at the speed of 50 tokens per second. It is around 10 times faster than the previous solutions using 7B models. And through the weight sharing and doubling the number of layers, the mobile LLM layer sharing version incurs only a 2.2% increase in the loading and the initialization time. This is uh, this this is benefited from the data locality. So in contrast, the model with double number of layers without weight sharing can exhibit a substantial increase, almost 10 times rise in the loading and the execution time. Mm. So furthermore, we also conduct some experiments on the chat dataset. We fine-tune the pre-trained mobile LM on the chat dataset and evaluate in the Alpaca eval and the MT benchmarks. As we can see in the table, the mobile model significantly outperforms the previous SOTA super-billion scale models like OPT, GPT, Python, and it can even surpass models with 1 billion parameters. And notably, this mobile 35 million layer sharing model achieves like an impressive win rate of 48% when comparing to the baseline GPT-3 model. Considering that the self-win rate of GPT-3 is 50%, so it's very close. It means the mobile 350 million layer sharing model is very close to the GPT-3 model already. Uh, and here we show some chart results of the mobile and this is a 125 million model, and it can like correctly respond to the user question and generating some reasonable answers, and so which means like for those easy tasks like chatting or API calling, we don't need the very large models. Small models can readily handle this very well, and we can like enable those chat experience by having a small model running on the phone or running on the wearable devices, and it can also preserve the memory. It can like save your battery by replacing the large models with small models. And this is another example. It can also like correctly answer the questions. Mm, okay, then we can go to the like SpinQuant paper. So before that, uh, any questions for mobile M, or shall we take the question after the boss presentation is over? Okay, if no questions, I will continue to go to the.
I
There
think
is a
there's
there
one
is
question.
Okay,
Hi, I have a question.
yeah.
So yeah, first of all, thank you so much for the presentation. It's great that we're able to like have an understanding of mobile LLM here. I think it's a great paper. Um, I just had like when I initially read the paper, I had this strong doubt was that I think in one of the appendices it said that distillation didn't seem to work for mobile LM, right? But somehow like Llama 3.2 strategy is highly dependent on distillation, and for them it seems to work. So what was the difference that made it work for Llama 3.2 and didn't make it work for mobile LM?
Mm, yes, that's a good question. Actually, like we tested the distillation performance for the mobile app. We also uh, include those results in the paper. I think the reason why it doesn't work for mobile app because the small models is limited in the capacity, like and it can hardly learn the similar representation as large models, and also um, we we can hardly let the like 125 million to model to mimic the 1B model's performance, or to mimic like 7B model's performance. So, so it is hard. It is hard to transfer the 7B model's knowledge into like smaller models, and I think the and I think the challenge is different. So that is one question, one problem. We cannot transfer very large models knowledge into very small models. The second challenge is like smaller models, um they are their major bottleneck is not the training algorithm, but it's their uh, inherent capacity. They can, because they are have very limited sizes, so they cannot capture very abstract uh, concepts. So so it is harder for them to uh, like learn better, even giving the better training strategy. And that's my understanding.
I see. So if I may just like take a second to rephrase, it's primarily because of the large difference in the parameters that the teacher and the student has. So let's say like 7B is too large for as a teacher for the 135 million and the 350 million mobile LLM models. Is that correct? Like,
Yes, yes, exactly. Like we tried like to use for example, one 7B to distill 1B, and 7B to distill 125 million, and 35 million to distill 125 million, and the later is slightly better than like using 7B teacher,
I
but
see.
still the improvement is minimal.
I see. Okay. Yeah, that makes a lot of sense. Thank you so much.
Thank you.
I had one follow-up, just so I can let
Sure.
you get to the presentation. Is to add to the distillation point, I was also curious about that. Um,
Mm.
so would you say that a distilled model, like if the gap reduced, say from 1B to 125, was there any benefit? So that was kind of like, was that something that was tried? And the sort of like the follow-up to that part is, was that also the large, like from what I understood from the presentation, there's a lot of changes in the architecture as well, right? Which sort of contributes to mobile LLM's performance. Do you think that also played a role in making distillation like less effective? So yeah, thanks for the
Yeah,
thoughts.
yeah. Good question. Like, I think we didn't spend much time in exploring the distillation. So uh, we just tried to use the 7B model as teacher, or use the 350 million model as teacher. So I think given like more available smaller models like Llama 3.2 1B, maybe we can like further investigate the distillation and see whether those good smaller models can serve as a better teacher than the like previous available larger models like 7B. Um, so I think that's a possible solution. And I think also smaller models, they are more sensitive to those architecture design rather than the training techniques. That's also one possible reason, as you mentioned. Yeah, but definitely, I think we didn't try much on the distillation. So maybe we can, as a follow-up work, maybe someone can also try more to see whether it can further improve. Yeah. Thank you. Thank you,
Thanks.
Harsha. Yeah. I saw another raising hand, Kayla.
Oh, hi. I had a quick question, which was, what was the difference between mobile LLM and mobile LLM LS?
Oh, the mobile LLM LS is just a layer sharing version. LS is short for layer sharing. So mobile LLM is without layer sharing. Yeah. So
I see. Thank you.
thank you. Okay. So let's move on to the SpinQuant work. So this is our recent work on LLM quantization. It is a very interesting idea that we use the rotation to reduce outliers, and it can lead to better quantized performance. So, so motivation is here. Many paper has observed that LLMs has a lot of outliers. Those outliers can be very harmful when we do quantization, especially like when we have outliers. It will stretch the quantization range, and it makes the quantization precision for those normal values to be very limited. So many previous works has started to reduce the outliers like SmoothQuant. It trades the activation outliers to the weight into the weight matrices and trades the activation quantization difficulty to the weight quantization difficulty. Instead, in this work we study a new angle of reducing the outliers, which is we reduce the outliers by rotating the weight or activation matrix. By rotating, I mean like we times the weight or activation tensor with a rotation matrix, which can like interestingly eliminate outliers in the network. And we can so like a vivid illustration of why this will work can be seen in this figure. For example, our original distribution is like in figure A. So weight tensor, we can imagine the weight tensor is a weight or activation tensor is a high dimension point cloud. And how we represent it is we just project it to the axis, and we got those numbers in both axes. Then we can represent the weight and activation values in the space. And there are various different ways to represent those weight high dimensional point clouds. We can like rotate the axis, or equivalently, we can say we rotate the point cloud. So in this way we can get a different representation in those axes, but we just represent exactly the same distribution or the same tensor. However, when we rotate those distributions, we can get more uniform or the more similar magnitude representation in those axes. We can see like for in figure B, by rotating the distribution by 45 degrees, the previously it has more it has larger magnitude in the axis 1, and which means this axis 1 will dominate the quantization range, making the representation position for the S2 be very limited. And if we rotate it, then those S1 and S2 has the similar range of representation, and we can then we can quantize them more easily, and we can fully utilize the quantization steps to represent both X1 and S2. They got both similar quantization positions, and in this way we can better quantize the values in the LLMs. And this is very interesting. In summary, in summary, it's like outliers only exist in certain bases. And by rotating the matrix, it can change the basis. And the random rotation, it can statistically make the projection of the tensor to each axis to have more similar magnitudes. And that's the basic idea why rotation can help reduce outliers. And to this point, we are discussing how we rotate a single matrix to reduce outliers in one single matrix. Then go to the LLM. It is a network. So how can we rotate the network how can we rotate the weight matrix and activation matrix in each network, and in the same time introducing as less rotation matrix on the fly as possible. So actually, the interesting thing is LLM is actually rotation invariant, which means we can rotate the shortcut path without affecting the output values. So it will output numerically identical values when we rotate the shortcut path, when every weights and activations are full position. How we do this? It's just in the input we have input X, right? And we just first rotate the embedding matrix by times the WE with the R1, and then its output, the weight is rotated out, and also its output is rotated. So the output activation, then the output activation goes into this first multi-head self-attention layer. And in this way, because there is a lot of nonlinearities inside the multi-head self-attention, so we will rotate back the X times R1, and in here we just got the same activation as before rotation. So all computation happens inside the self-attention as identical to without rotation. And after doing the computation, we just rotate it again to add to the shortcut to make sure that its output and the shortcut are at the same basis, so they can be added together. And similar thing we do for the feed-forward network. We just rotate it back and do some nonlinear computation, and we output the same identical outputs as without rotation, and then we rotate it and add to the shortcut, and then we just pass it to the output layer by rotating it back. Then in this way, we can get the identical outputs as without rotation. And in this way, then how it can reduce outliers and how we can absorb it to the weight matrix to reduce overhead. We can see it here. Because activation quantization happens here, it's like we are quantizing the rotated activations. So it's X times R1 getting quantized here. So there are 5 layers can receive easy to quantize activations, including WQ, WK, WV, and WF and WGate. Those activations here, those input activations, they are quantized and they are rotated and they are easy to quantize. And also we can just absorb the R1 with the embedding weights first, and those R1s can be also absorbed into the corresponding WQKV, and those R1 minus 1 can also absorb with the WF and WGate. So every R1 can be absorbed into the corresponding layer. So R1 did not introduce any memory overhead or any latency overhead. We can just rotate it offline and store those rotated weights instead of storing the original weights. Then it becomes easy to quantize. And the nice thing is it's not trading the quantization difficulty between activations and weights. The rotations can help both activations and weights at the same time, because when we rotate the weights, its activation output simultaneously got rotated. So both weights and activations become easy to quantize. And to this point, we already deal with WQKV and WF and WGate input activation. And what we didn't deal with is the WO's input activation and the WDown's input activation. So similarly, we just rotate its activations and W2 can be absorbed into the previous layer WV, and its W2 also didn't incur any overheads. And for the W4, it cannot absorb into the previous layer, so we use the online Hadamard rotation, which we will introduce later. So the online Hadamard rotation didn't it's fast to compute and it's small to store. So similarly for the KV cache quantization, we also use online Hadamard rotation R3 to rotate the key and the value before quantization. Let me see if there's any questions now. Okay, so maybe we will continue. Like we can, so we propose two models. One is SpinQuant no Hadamard, another is SpinQuant Hadamard. So SpinQuant Hadamard no Hadamard means we only use R1, R2, and it can merge the rotation matrix into the pre-trained weights without altering the network architecture. We just store those rotated weights, and it is suitable for the low bit weight quantization. It can already achieve a boost accuracy for the W4A8 quantization and W4A16 quantization. And for the harder scenarios, which means we want to quantize the activations or KV cache into lower bits, like 4 bits, we can use the SpinQuant Hadamard, which use all the 4 matrices, and the R1, R2 are mergeable, and R3 and R4, they use the online Hadamard rotation, which is fast to compute. And we can use this for those W4A4, W4A4, AB4 settings. So there are different types of rotations. As we mentioned, there is like random floating point rotation, which means we just make the matrix orthonormal. Then it is a rotation, random rotation matrix, and we can use Hadamard rotation. Hadamard rotation is a special rotation matrix. It is formed with -1 and 1, and it's times some scaling factor, the square root of number of elements. And we can also construct a random Hadamard matrix by times each row of the Hadamard matrix with random -1 and 1. In this way, we can construct a random Hadamard matrix. And we have many fast Hadamard kernels, and it can compute the online Hadamard with high speed. So then we start investigating how those different rotation matrices affect the accuracy. We can see the random rotation matrix, it will have a large variance, like bad rotation matrix and the good rotation matrix can have like 15 points difference in the zero-shot accuracy. And the Hadamard matrix is it is better and with smaller variance and overall higher accuracy than the random rotation matrix. This is a very interesting phenomenon, and we can briefly get an idea from this illustration. For example, Hadamard we can view as uniformly rotating all axes by a certain degree, and it can spread the distribution more evenly across each axis, and it can achieve better accuracy than the random rotation. Well, if we take this further, because the distribution inside the network is not black box, we know the distribution, so we can actually optimize those distributions, optimize those rotations to make the distribution easier to quantize, and we can, based on the distribution, we can find out a more optimal rotation that reduce the quantization error further than the Hadamard. So in this way, we propose optimization-based rotation, which is here we use an K-lay optimization to optimize the rotation, and it achieves like much better accuracy. It achieves smaller variance and better accuracy than all the random rotation and Harman rotation. So how we do this optimization? We set our optimization goal as the quantization loss of the network, and we optimize objective is R1 and R2. We only optimize R1 and R2 because they are absorbable. They can be any rotation matrix, and R3 and R4 they are just they need to compute online. So we keep them as Harman matrix for fast computation. So we the think we can simply optimize it with scaling HGD. We will not go into the details of the scaling HGD. We can just know that scaling HGD is an efficient optimization algorithm for optimizing a rotational matrix while keeping its orthonormal property, and it can update the rotation matrix and on the stateful manifold. Yeah, and it's just the mechanism is like doing some projection. It will project the gradient update back to the stateful manifold, and then it can keep the rotation matrix to be orthonormal during the optimization. Then after doing the optimization, we can see that the SpinQuant results, SpinQuant achieves much better results than the previous works without rotation, such as GPTQ, LLM-QAT, and it's in the for W4A8 settings, like the SpinQuant no Harman can already achieve very good accuracy. And in this case, we can just use R1, R2, and it introduce no overheads in the inference time. And for the lower bit quantization in activations or in KV cache, we can further utilize the Harman rotation R3 and R4, and it can further boost the accuracy. And this W4A4 case is very hard for the previous methods, and it can hardly achieve satisfactory results. And with learned rotations, it can boost accuracy by like 10 to 20 points in the short accuracy. And those are very good method to try. So we also show these ablation studies to see how learning rotations can help to increase the accuracy compared to random rotation. We can see that compared to random Harman rotation, the SpinQuant SpinQuant method, even with R1, R2 or with R1, R2, R3, can consistently boost the accuracy by 2 points to like 15 points. And also the SpinQuant is compatible with GPTQ, and the interesting thing is like we find GPTQ is optimized for weight quantization. So when we optimize the rotation, we will just targeting at optimizing rotation for the lower bit activations, and we just keep the weight to be 16 bits, and we just optimize the targeting the quantization bits to be 16 W16 A4 and KV4 something, and in this way we can boost the accuracy when it's combined with GPTQ. And that's basically all for my presentation. Thank you. And any questions?
I could go first. Thanks a lot for the talk. I actually really liked your paper as well. So
thank you.
So I had a couple of questions. I'll try to get them out in one way so the others can ask as well. So in terms of like the W4, A4, do you actually have like a in4 kernel which is like running the operations there, or what would be the precision of the dequantization in that case?
Yeah, good question. Because we are mostly using the H100 to for our experiments. So H100 it supports the FP8 kernels. It doesn't it don't have int4 kernels. So currently we are using W4 the W8 WFP8 AFP8 kernels for the experiments for the GPU speed experiments. And when we got like a B100, we will test speed on like WFP4, AFP4 speed because B100 supports FP4 tensor core kernels.
I'm actually curious about that. So I think Carrot, which is like concurrent work, which you mentioned, I think is they do roll out like. So is there any choice other to not use int kernels rather than FP kernels?
Okay,
Like,
question. First, the Quarrels, their kernels is CUDA core. So there's
right.
two different versions. One is CUDA core, another is Tensor core. So Tensor core is like 50 times faster than CUDA core, and so we if we want to use it in production, we need to use Tensor core. So we didn't invest much on CUDA core. We only invest our time in the Tensor core kernels.
Okay, that makes sense. And the last question is there like a question that's coming up for me frequently is that how does the impact of quantizing the KV cache sort of propagate across the precisions? Like in the sense, like I'm sure you evaluated at 8-bit, 16-bit, and then 4-bit. Like what are the benchmarks where that showed up the most? Like in the sense, like where it was very obvious that quantizing the KV cache like this with hard mode or without SpinQuant, where did the impact show up the most? I was just curious about that.
You mean like how quantizing, comparing without Karmat and with Karmat, how it affects KV cache quantization?
Yeah, progressively, because you're going lower and lower precision in the KV cache, right, as we progress. So what evaluation on metric did that sort of impact the most? Is there any sort of exploration in that direction?
Oh, you mean like on which benchmark we see most difference?
Yeah. And did it like change with size also? So I was curious about that. Yeah.
Good question. Actually, we didn't study this partly because we mainly focus on the activation outliers. So KV cache may relevant to those long context scenarios, and I feel like my intuition is like a task with longer context might be affected more with KV cache quantization or KV cache compression. But I didn't do much experiments on this part.
Yeah, but thanks a lot for all the answers. Once again, it's really cool work. Thanks.
Yeah, thank you for this question.
Hi.
Hi.
Hi, thank you for the talk. So I just have a really quick question. That is that all the figuring out the effect of the quantization is focused on higher source languages? Is there any benchmark tested on the lower source language or mid source languages? Is there any detection for this?
Good question.
Is it explored?
So by lower source language, you mean like other language other than the English, or?
Yes.
We didn't test on those small other languages. So you mean like if the languages it has little pre-training data, they might be affected more with the quantization.
So am I just feeling like this all SpinQuant is focused on the English language, like benchmark are focused on the English language, so there no other language has been tested in this experiment or in this research.
Yeah, I get your question. So I think like the number of training data sets of it affects more in the pre-training phase, and if we because SpinQuant is a post-training technique, it requires very minimal calibration data sets, so it won't be more it won't be affected by the number of training data available on certain language. If the per it I'm I mean, like the number of training data available might affect the model quality,
Mhm.
but when model quality, we already know the per training phase how it performs in accuracy. SpinQuant won't change much based on the per train accuracy because SpinQuant is doing some calibration only. It doesn't require the data. It doesn't require much data for that.
Mhm. Mhm.
Yeah.
Thank you.
Okay, thank you. Mm, okay. So, if we don't have any further questions, we can maybe stop early.
Yeah, thank you so much for the session.
Okay, thank you so much. Thank you so much for
Thank you
Yes,
very
yes.
much.
hosting and listening. Yeah, thank you.
Yeah, last question.
Okay.
I mean, yeah, how to reach out to you? I mean, what's the best
Oh,
source to reach out to
you
you?
can you can send me the email. You at
Oh,
like my Zechun at meta.com.
okay. Thank you.
Okay, thank you. Thank you so much.
Thanks.
Bye.
Bye.
Thank you. Bye.
Thank you. Did you say it was just your name at meta.com?
Yeah, my name, just my name. My first name.